Alright, so this is the 6th installment to our forces unit. So there's quite a few parts to this unit, but they're all very related and they just build on each other. So now we've talked about the tension force, we've talked about Newton's laws. Now we're going to talk about probably one of the biggest byproducts of Newton's third law, known as the normal force. So let's think about a box. It's just sitting on a table, the forces that are involved, which include Fg pulling down on the box, pulling the box down. Another force that is going on here, so we can Fg, we would have the box then applies a force to the table. And that's just because if you think about it, the heavy box putting on the table. So we get a force. So we get a force on the table. And a third force. Now the third force is based on Newton's third law. So according to third law, the table then must push back on the box, which we talked about last class. Back to box. And so we get this force up here. Now we are going to give this a name. We are going to call this force the normal force. And we're going to give it Fn. So no longer is it just like the force of the table. We're going to specifically call it the normal force. Now if we think about this situation, the box isn't moving, so we know the F net is going to be 0 newtons. So for this situation, a box not moving, the normal force is going to equal gravity, because that's the only way, the only forces acting on the box, so they have to be equal to balance out. But that's only in this problem. We can easily change the normal force. It's not always equal to gravity. And here's an example. So if I push down on the exact same box, our free body diagram now includes force of gravity, my force applied going down, and then the normal force has to get stronger because the box isn't going through the table, it's still there. So the F net is still 0 newtons, and it just changes because now we've got 3 forces instead of 2. Fn will be positive minus Fg minus F applied is still going to be equal to 0 newtons because it's not moving. And this would tell us then that the normal force would be equal to the force of gravity, which it was before, but also to the force applied added together. So the normal force got bigger because there's more force being applied down. So that's what's interesting about the normal force, is that it can change. It is only as strong as it needs to be, and every surface has a maximum amount of force that it can give back. If the force applied to it exceeds that, then the surface will break. Normal, now it's not like it's just a regular force. Normal, it actually comes from mathematical terminology, meaning perpendicular to the surface. And that's what a normal is. So we only get this force when two things are in contact with each other. So a surface on another one, we have to have a normal force when that happens. And this force, the normal force, will always be perpendicular to those surfaces. So if you're on a table, it will always be straight up. If you're against the wall, the normal force will actually be straight out from the wall because it's perpendicular to that surface. And as I said, the force that the normal force has will always change depending on the situation. So it's interesting that it can change. And now let's look at an example of calculating it. So we've got a helicopter accelerating upwards, so we chose upward to be positive. What lift force is exerted by the air on the propeller blades? So helicopter blades are spinning. It applies a force to the air downward. So it pushes air down. That's what helicopters work. Push the air down. That air then pushes a force back up, causing lift. So that would be a normal force acting on the helicopter. So our free body diagram has Fg, force of gravity on the helicopter, pulling it down, and then we've got the normal force pushing it up because it's applying a force to the air. It's not the force applied because it's applying a force on the air. The air gives the normal force back to the helicopter. So, starting from the exact same spot, F net equals ma. Always the same spot. Add our vector forces. Get rid of our vectors, add in our directions. Up is positive, so we get Fn minus Fg equals ma. Our goal here is to get Fn, so Fn is going to equal ma plus Fg. We know that Fg is always equal to mg, so then we have to just plug in our numbers, 4,500 kilograms times 2.0 meters per second squared, plus 4,500 kilograms times 9.80 meters per second squared. And that, in our calculator, will give us 53,100 newtons. Carefully look at our sig figs. It's going to be 2, so we get 5.3 times 10 to the 4 newtons. So the problems are exactly the same as we've been solving. All we have now is a name for that force that objects exert back onto us, the normal force. So there's a normal force acting on you from the chair that you're sitting on, from standing on the floor. That's the normal force pushing you back up. If you lean against the wall, that's a normal force that pushes back on you from the wall. So we just have a name for it. It is not a new force. We've just given it a name. And it's important to remember that the normal force can change. It's not always the same. It changes with the situation, whether it needs to be greater or less, just so, because it only does what it needs to. And that's why physics is awesome. So take a look at these problems. A couple in the textbooks will be number 38, 75, and 80. And enjoy.